Hello everyone and welcome to an exciting video about the plane, the wedge, and the screw. The first three simple machines that we learned about yesterday. We're now going to go into a little more detail and do some calculations. So we can see that, I'm going to escape out here and make sure I got, that'll be work so I can grab my ink. Okay, please tie to your notes, 5-2 plane wedge screw. We're going to get started here in just 1 second. Pause the video if you need to. We're moving on. Here we go. Okay, we talked about yesterday how simple machines can make work easier. The example I gave was people eating an entire pizza. You still have work to do when you eat a pizza. It just becomes easier or harder depending on how fast you do it. Or I guess a couple other factors too. But it's the speed, and that's where we're going to we have a trade-off, the difficulty of consuming that pizza. So it turns out simple machines never actually change the amount of work that's done, mathematically speaking, only the rate or difficulty at which the work is done. So if you take a look at this example down here, we've got what appears to be, let's see, grab my black, or let's do blue. Oh no, there we go. In blue, we have our first example. Here you've got 20 newtons moving, a force of 20 newtons moving 1 meter would be the same as moving a force of 10 newtons moving something 2 meters, so on and so forth. It doesn't matter what you do. They all end up being the same amount of energy used, which is 20 joules. It just turns out that when you're applying this big force, it's too much. I mean, it can be too much for us. This can be difficult and just not comfortable, too hard for us to accomplish. When we have the machine at our disposal, you can be happy because it's a more swallowable chunk. I think to that wheelchair ramp. What's easier, going up a flight of stairs or going up a wheelchair ramp? Well, it depends. Wheelchair ramp takes longer, but it's less work at any given instant. So that's how we can use machines, and we're going to be able to calculate exactly how much easier, or roughly how much easier, these can be. Here we go. Okay, first simple machine is the incline plane. Its job is to transfer load over a long gradual incline. There's the trade-off, rather than transporting over a much shorter vertical path. So rather than trying to scale this cliff, going all the way up and down, typically, and you see this with a lot of backcountry skiers or people that are going up a steep mountain, you do these switchbacks, right? You come up and you're just doing a quick turn, going straight. It makes this a much easier way to get up something that's very steep. Going back and forth, it may take longer, but maybe it's the only way that you can get that accomplished. Okay, so over a long gradual incline rather than transporting over a much shorter vertical path. So I'm calling this the slope length, and some of these problems you have to make sure you know the difference between the slope length and the actual length. The length would be this distance here, and this is a right triangle. That's our length here, this is the slope length, and they are considered different. So the mechanical advantage, the trade-off that we can quantify, is always the input divided by the output. So the slope length, the input, what we did, divided by the output, what we actually accomplished. So we went up this slope, okay? What we actually accomplished against the force of gravity was this height here. So we're going to do the slope length divided by the height. Input divided by output, the height. Let's see an example so we can do some calculations. You want to lift a circular pillar up onto a porch. The inclined plane you use is 18 meters long and your porch is 1.5 meters high. What mechanical advantage does your ramp provide? Okay, so let's draw the same thing that we kind of had going on before. I've got a ramp here. Going up, it looks like it's 1.5 meter high, and this is not necessarily to scale. Here's my porch, got a ramp going up, and I know that the slope length is 18 meters long. So we want to find our mechanical advantage. Remember, that's input divided by output distance for mechanical advantage. So we come down here and we can say MA is equal to, our input was what we did, 18 meters. Output was how high we ended up going, which was a total of 1.5 against the force of gravity. So you guys can get out your calculators, do 18 divided by 1.5, which I think is, let's see here, times 2, 36, divided by 3, 12, I believe. So we have a mechanical advantage of 12. What that means is we have, it is 12 times easier at any given instant when climbing up this ramp than it would be trying to go up this ledge here. Okay, it's 12 times easier, but it's forcing you to go 12 times the distance. So you have a trade-off for distance and really a trade-off for time as well. So taking longer, both distance-wise and time-wise, to get that accomplished. So that's what we're going to write down here. How do we interpret a mechanical advantage of 12? What does this mean? This means, number one, let's go ahead and change colors for fun's sakes. Okay, let's see. The first thing that it implies is that this is going to be at any given instant the force we apply going up the ramp will be 12 times less. Okay, that's the first thing that it implies. The second thing that it implies is that after we've completed the job, we will have traveled 12 times the distance and taken 12 times the time. Well, I think that's not too terribly bad of a trade-off. I know things just take longer when you're getting up there in age, which I am not. Okay, so don't pick on me. But anyways, what I'm saying is, let's scroll on up here. Let's take a look. It looks like we've got a pretty simple, straightforward question so far. Let's see one that's maybe a little bit more challenging. Going on to the next example. Find the mechanical advantage of the inclined plane below. This is that picture from yesterday of the pyramids. Okay, let's say this is 123 feet. I just made these numbers up. I don't know if it's to scale. And 435 feet. And we want to find the mechanical advantage here. Oh, I saw what you did. You wanted to do 435 divided by 123. Not going to work, Buster. Here's why. Remember, it's not the length, it's the slope length. Oh, dear. Oh, heavens. So we need to know this distance. But I didn't tell you that distance, which means we're going to have to use one of my favorites. First, we're making some assumptions here. We have to assume this is a right angle, and we're looking for that distance there. Okay, this is a right triangle. We know this leg and this leg of the right triangle, and I hope some of you have muttered this already, but this is the Pythagorean theorem. So if you know the two legs of a triangle, but you don't know the hypotenuse, we're going to call that C, okay, you can use the Pythagorean theorem to help you calculate this. So here's what you do. All you got to do is, Pythagorean theorem says, leg squared plus the other leg squared is equal to the hypotenuse squared, which is this distance here. We know that A is 435, so this is 435 squared, plus B, which is 123 squared. And we don't know C, so we have to leave that as C squared. Continuing on down the line. Okay, we need to do some numbers here. 435 squared is a big number. It's 189,225 plus 123 squared, 15,129. Man, that seems, first one seems way, I guess not. Wow, that's crazy. Okay. And we know that that is equal to c squared. It's hypotenuse squared. So we're going to add those two numbers together, 189,225 plus 15129, which is, you get a total of 204,003, oh dear, 204,354. That's c squared. Okay, so now we want to do our calculation here. In order to solve this equation, you have something squared equal to some number. So what times what equals 204,354. And to get that, you just have to use the square root. So I'm going to raise that, do the square root of 204,354 to both sides, and you'll get c is equal to 452.06, and that's in feet. Now, I'm going to tell you right now, the Egyptians would not be using feet. People are probably making fun of me. I don't know what they'd be using, cubits or something crazy. Anywho, we're still not done. That was just the pre-work so we could get the work started. So now I got to go back and I got to say, all right, so I got to figure out C, which that's the slope length that I want. We know C now is 452.06, and we're going to divide by the height output to get our mechanical advantage. So I'm going to come on down here and I'm going to say, all right, my mechanical advantage is equal to 452.06 feet divided by 123 feet. Feet cancels with feet, and you just end up with 452 divided by 123. Yeah. This provides us a mechanical advantage of 3.67. Is that rounded up? Sorry, I got a text message here. 68 rounded up. 3.68, which means then there's no units. This is not feet. This is your answer. This is your mechanical advantage. Okay, that means it is 3.68 times easier to go up that slope than it is to try and climb up the face or try and go up a vertical path. Okay, it also means that you're going to have to go 3.68 times the distance. And probably going to take 3.68 the time. Who knows? Maybe it'll take less time. Just depends on your method. Anyways, there's another question. Let's go on to the next simple machine. Get things cruising. The next simple machine is a wedge. It comes in many forms. I like some of the examples you guys thought of in class. Specifically, I thought the syringe was really cool. That's a great example, and there's a couple other ones as well. Meant for dividing material. It converts forward force, that's this blue line here, forward force into outward force, the green lines. Okay, don't be like Captain America here. He's working too hard. All he needs is one of these or maybe a splitting maul or something along those lines. The mechanical advantage for a splitting wedge is the, again, it's the input distance divided by the output distance, just like it was before. The input is the same as the forward force, right? The length that runs that same distance. So the input is the length. The output is what we get when we separate the logs. Once we're done, the log is this far apart or whatever it is that we're splitting. So to calculate mechanical advantage, it's pretty straightforward. You just need to know the length and the thickness for a wedge, and you can figure out how many times easier it will be to separate material. Moving on to the screw. The screw is interesting because it converts rotational force into linear force. So you're taking something that's turning and it's moving the screw up and down. I mean that's pretty sweet that you can change direction to move things up and down. I think it's amazing. Input distance, output distance. This one's not as straightforward for understanding. I feel like just using the formula will be helpful. It's pi times the diameter is your input distance, which is basically pi times the diameter times pi is the circumference. So your input distance is kind of the distance around the screw, and your output distance is the pitch. So the pitch is the distance between these two levels, okay? times pi. Yeah, that's just the circumference. Interesting. Pitch is the difference between it's one full revolution. So if you're going around this, it goes around the back side, wraps around, and comes back. So the distance between one revolution, you can, on like Autodesk Inventor, when you're threading a screw or you were coiling, you could very easily control the pitch when you were choosing. So pi times the diameter divided by the pitch. Let's go ahead and do an example here. The screw screw below provides a mechanical advantage of 7. Its diameter is 10 millimeters. What's the pitch? Oh, Lord. Okay, so we know the mechanical advantage in this case. We have a little algebra to do. The mechanical advantage, remember, is mechanical advantage equals pi times the diameter, which is 3.14 times the diameter, d, which we know to be, I'll just write it out one more time, the diameter d divided by the pitch. And we don't know what the pitch is, so this is going to be a little funky. So I do know what the mechanical advantage is. It says that the mechanical advantage is 7. So 7 is equal to 3.14 times the diameter. The diameter is, cha-cha, 10 millimeters. And we don't know what the pitch is. I'm just going to use P for everyone if that's okay. So we got a weird equation here to solve to figure out the pitch of our screw. So what we're going to do to get this done is we've got an equation. We have to solve for P. It's on the bottom, but we do have a proportion. So we're saying 7 can be written as a fraction of 7 over 1. I've got some number up here, 7, 1, and P on the bottom. So we're going to use the cross product property to solve this. So multiply along the diagonals. Everyone should have seen this so far, hopefully, in high school and middle school. Multiplying across the diagonals, P times 7 gives me 7P equals, in blue, along the diagonals here is 3.14 times 10 times 1. Multiply along the diagonals, it's equal to 31.4. Okay, and now to solve for P, all we have to do is divide both sides by 7. 31.4 divided by 7 is, calculating, Lego bot calculation, 4.P is equal to 4.486, we'll say. So the pitch is 4.486, and it's going to take whatever the units of the diameter were, which is millimeters. Great. So we just use the mechanical advantage equation to calculate, not mechanical advantage, but something else, the pitch. Super. Awesome. Let's go ahead to the next. I think we're actually almost done. Let's take a look here. So one comment is when we're doing these things in theory, like we're calculating the mechanical advantage for splitting a screw or a wedge or climbing a plane, that's under perfect circumstances, and that's called ideal mechanical advantage, and that's not necessarily realistic. So you have your ideal mechanical advantage over here. So I just make a note. This is not realistic. This one is realistic, so our actual mechanical advantage. What are some of the factors that prevent them from being the same? Okay, so what makes it, what makes a wedge maybe not as efficient as another wedge? And a lot of things could be, things like sharpness of the object we're using, if this is for like a wedge. If you guys probably think of a couple other things that make ideal mechanical advantage not the best. Friction or lack of friction, right? Maybe walking up an inclined plane might be really, really tough because it's slippery, or might be really, really, maybe it's there's friction between a wedge as it's passing through the material. Maybe it's a rough material that's causing friction. So ideally, or things like wind, right? Things that can make things imperfect. That turns your ideal into an actual mechanical advantage. So basically, this is always going to be bigger than that. due to these things and maybe other things that you've listed. If there's something else you listed with the class that sounded good, go ahead and write that down. That are going to get in the way of making it perfect, making it the theoretical one that we're hoping for. So things aren't perfect, but we can get pretty close. Okay, and that's it. So thanks for watching the video. You guys have the remainder of class and time to work on the assignment, and please turn that into the sub when you are finished or put it in the box. Thank you very much for watching. Hope you guys have a great day.